Alright, so this is the Baker Hughes challenge for TAMU Datathon 2024. To first start off, I just want to talk about the inspiration for this project and why we took it. So we felt that this project prioritizes a new challenge because it deals with a significant real-world impact. Monitoring electric motor health is vital in industries like manufacturing, oil and gas, and energy. And leading companies like Baker Hughes need advanced machine learning models to address these key challenges, to help minimize safety hazards and other things that they might be experiencing in their day-to-day lives in their industries. So we chose three different ways to do this, calculate our data for this machine learning model. The first one was grid-based. So from the initial data given, we wanted to create the best possible sampling algorithm that fits the criteria of selection number one in the challenges. This is where the data should be reduced to 2,500 data values that are distributed uniformly across the region so they can be trained equally. We decided to use a grid-based sampling algorithm as our first one, which with a predetermined number of bins, we can cap the amount of values for each bin and try to get as close to a complete uniform distribution as possible. Specifically, we had to have used 50 bins. We had 50 bins, and each bin had 50 data points. And as this resulted from both data sets to set a very close uniform distribution. We can really see this effect with the provided histograms from the second data set. The data tend to really cluster later in the values, but the uniform distribution model appropriately compensates the lower end of the values, giving us a much more balanced data set compared to the original data given. The challenge that we face with grid-based data is that finding an appropriate number of bins and values per bin while also considering compilation time. To give you an example, a higher bin count could potentially provide a better uniform distribution, but the compilation time greatly increases and might result in output errors. Alright, so the second algorithm that we used is a cluster-based, or as some might call it, a density-based algorithm. And this fits the criteria of selection number two in the challenges. This requires us to still have a good level of coverage within the entire data set, but favor data points where the original data set has a high density. Because the high density regions are where the asset is mostly operated, using the algorithm to find appropriate data training will greatly improve overall training quality across more regions and offer better predictability results for the health of a motor. For this criterion, we decided to use a density-based sampling algorithm. This unsupervised algorithm heavily prefers denser regions by assigning a higher probability of selection to data points located in those clusters. By doing so, it ensures that the model receives more information from the most commonly operated conditions, thereby improving its ability to predict performance and detect anomalies in these critical areas. At the same time, the algorithm still ensures some representation from less dense regions to maintain overall coverage and removes blatant outlier data to prevent skewed regions. In this case, we decided to save computational resources by removing blatant outlier data to prevent skewed results. To save the computational resources, we made sure to limit our cluster analysis to 10,000 points per dedicated cluster. Visualization in the histograms really shows the similarity with the original data and between the original and the density sampling data. The algorithm that we used was interpolation. To give you a simple idea, it's just a combination of grid-based and density-based. For interpolation, we wanted to incorporate a user input so that they're able to gradually change the desired distribution using a parameter alpha that goes from 0 to 1, where 0 is completely grid-based sampling and 1 is completely density-based sampling. Depending on what the user wants, they can pick values in between in order to have a gradual change from the one distribution to another. We compared linear interpolation and radial-based function interpolation, or RBF, to determine the most effective method for predicting motor health. Linear interpolation estimates by drawing straight lines between adjacent data points, while computationally efficient and simple to implement. It struggles to accurately capture complex nonlinear patterns, but linear interpolation often results in piecewise linear segments, which can lead to sharp discontinuities and an often oversimplified model that may miss subtle trends in the data. This is where we began to shift to RBF interpolation. This uses a smooth continuous approach by fitting a radial basis function to each data point and combining their influences to estimate unknown values. This method excels at capturing nonlinear relationships and provides a smoother, more accurate approximation of the underlying patterns within a dataset. Right. So now that we have our data, we now need to visualize it. Our code for the visualization section creates two sets of 2x2 figures, each comparing our grid-based, density-based, interpolated, and our relational data sets. The first set is our plot, which illustrates how each data set is structured. The top left plot shows grid-based data in blue, representing a uniform spread across the value range. The top right plot displays density-based data in green, emphasizing high-density regions where the acid operates frequently. The bottom left shows interpolated data in red, blending grid and density characteristics using an alpha factor. Finally, just for your convenience, we add the original data in purple on the bottom right, which serves as a reference for sampling methods. The second set of figures is our histograms that displays the distribution of the x1t variable across these datasets. Here we can see the sampling method which affects x1, well, actually both x1t and x2t variable across the datasets. Here we can see how each sampling method affects the x1t and x2t frequency density. By grid-based data, which remains uniform, density data emphasizes cluster regions, and interpolated data creates a balanced blended distribution. These visualizations help us compare how each method captures and represents the underlying structure and trends in the data. The graphs were also normalized as the range is bounded by the frequency density to involve a swift and fair comparison between the different datasets. Alright, so just to cap things off, in conclusion, we first just want to extend our gratitude to Baker Hughes for providing us a unique opportunity to work with their real-world data to develop a machine learning algorithm. This experience offered us unique insights to how a leading company leverages data analysis and machine learning to tackle present-day challenges, and I just want to thank them for giving us this opportunity.